Okay, so this video is to supplement the parts that we didn't cover in the lecture, which is about mathematics related to the electromagnetic inductions. So let's have a revision first. Electromagnetic induction. So the idea here is that we need to ask, we need to study when will be the situation that the EMF is induced. So our final, the final ultimate result is that we have a EMF induced. When you have a EMF induced, then we could, if the circuit is closed, then we will also have currents to flow. And then we will be asking a question like, okay, then in which direction of the current will flow? So therefore that leads to the idea of Lenz's law or Lenz's law, which tells us that the direction of the current will be to oppose the change that causes it. So therefore, the very important starting point will be the induction of the EMF, or like when EMF is induced. And to get that happened, then Faraday did a lot of experiment, and then he find out that there are like two possibilities that the EMF will be induced. Essentially, we need something to change. One possibility would be I need to have a cutting of magnetic field lines. So this cutting of magnetic field lines can happen by having a moving conductor in a magnetic field, or we can have a moving magnet in the neighborhood of a conducting wire. So we need some motion so that there is a cutting of magnetic field lines. So one very good example, let me use the same color. One very good example would be you have a solenoid. You have a bar magnet. And then from previous chapter, we know that there will be there is a magnetic field carried by this bar magnet. And if you, for example, you can move the magnet back and forth, or you can also move the solenoid back and forth. Then this kind of movement will result in a cutting of magnetic field lines. So there will be an EMF induced in the solenoid. Well, another possibility that we can have a cutting of magnetic field lines will be when a certain coil, we will study that when you have a coil, we usually have some magnetic field lines in it. Let's say like this. So for example, I have some free magnetic field lines in such a coil. And then it turns out that when there is a change in the number of the field lines, for example, you say this is like a before, and then there is like an after. Then after there is just like two field lines there. So there is a change in the number of field lines in loop. Then there will also be a EMF induced. So there will be the second possibility, that there is a change in number of field lines enclosed by the loop. Right? Sometimes it is easier to visualize a situation using a cutting of magnetic field lines. Sometimes it's easier to visualize a situation or to understand the situation by thinking about the number of field lines enclosed by the loop. But in fact, if you are careful enough, you will see that actually these two are related, or these two are equivalent. Because when you have any cutting of magnetic field lines, then there must be a change in the number of field lines enclosed by the loop. It will be easier to see in this way, is that I start with this kind of perspective. So what happened is you have a change in the number of field lines. But field lines cannot be suddenly disappear. You could not just like, oh, I delete these field lines, therefore I have only 2 field lines left. In reality, field lines cannot be just deleted. What happened is you can only like move these field lines away, so that the field lines are separated from each other in the case of, let's say, a weakening magnetic field. So therefore, when you turn a before to after, so that you reduce the number of field lines in the loop, essentially during this process, you must have one field lines cutting the loop. So that means there must be a cutting of magnetic field lines occur. So therefore, you can see these two are actually related. But the textbook, and also I will also suggest students to be aware of these two, because it's really sometimes it's not that easy to visualize the situation using this point of view. While cutting of magnetic field lines will be a easier way, but it turns out that mathematically, the expression we're going to talk about next will be more related to this part. Now, okay, so this is essentially what we have discussed in the lesson. It can already apply to many different cases. However, it's not complete because in fact we are able to use mathematics to talk about this kind of physics here. Well, the mathematics here we are going to use, this situation is something like Newton's law. Newton's law, you can use Newton's law and then apply it to many different situations without using mathematics. But of course, the power of the Newton's law is that actually you can do calculation, you can make numerical predictions. So the same thing happening here for the electromagnetic induction. We're going to talk about the mathematics of the electromagnetic induction, and then so that we can do calculation on the EMF induced. So let's put it. Let's introduce the language we need for the mathematics to be put in. So the things we are going to talk about now is the so-called magnetic flux. The symbol of the magnetic flux is this letter. It's polarized as phi, like this. So the definition of the magnetic flux is the following. Phi equals to B times A times cosine theta. When we talk about a magnetic flux, we usually refer to a loop. So this is the magnetic flux of a loop. The loop we're referring here, you can just think about it like a circle. And let me draw here, so like a loop. This is the loop. And then the unit of the magnetic flux is defined as a Weber with the capital W and lowercase b. So according to the definition, it should be the magnetic field strength multiplied by the A. And then when you talk about a loop, then the area you can already guess it, which is the area of the loop. So this will be the area A. And then you got some magnetic field. This magnetic field may not really going through the loop in the sense that it's perpendicular to it. We do like this. So you can think about, I got a magnetic field. That magnetic field lines that go like in this kind of direction. Okay. Like this. So this is the magnetic field B. So this is the magnetic field strength. And as usual, the unit of magnetic field strength is Tesla, and then A will be the area of the loop. And then we use the meter square as the SI unit. Now then finally, we've got a theta here. And for theta, referring to this kind of diagram, you may visualize this in the case of like reflection or refractions. Although these are like the magnetic field lines, but if no one tells you that we are in the topic of magnetic field, you may mistaken this as just a ray diagram that we have learned in the topic of waves. And in fact, this is true. The corresponding theta is defined with respect to the normal of the area. So I got an area here, and then we got a normal. So with this one, maybe we could use this color less transparent. Is like this. Yeah. So we are talking about the angle between the normal of the area and the magnetic field lines. Just like what we did in the past, the angle is divided between the ray and the normal of the boundaries. So then this is the corresponding theta. Okay. So this is the angle between normal of the loop and the field lines. And then in a unit of degree, or degree is not unit. Okay, now this is the meaning of these definitions. So let's study a bit about this definition so that we can develop a intuitive understanding of what is this about. First of all, we will immediately see if I have a stronger magnetic field, then I will have a larger magnetic flux. Well, or if you have a larger area, then it means that we have a larger magnetic flux as well. So essentially, the magnetic flux is proportional to the magnetic field in the area. And why is this the case? Well, we could introduce this kind of intuitive understanding. So intuitively, what is magnetic flux is doing is that it is trying to measure, I just use the term flux. Flux is a measure of the number of magnetic field lines enclosed in the loop. So for example, I have a region of magnetic field lines. then I can have a different loop present in the question. Now I think I particularly use this color, yes, and then I introduce different loops. And for example, I will have the first loop that is enclosing only this part of the magnetic field, and then I enclose another loop which is much bigger, that it is able to enclose all of these 6 magnetic field lines. So therefore, comparing loop A and loop B, then the number of field lines that is enclosed by the loop is bigger for the second case. So therefore, the phi of A and the phi of B, then we'll say phi of A is bigger than phi of B. I use the uppercase. It is. So therefore, it makes sense because now you are using a bigger area. So therefore, you of course get a more number of field lines enclosed inside the loop. So the magnetic flux is stronger. Now, however, if I have consider another loop which is bigger than the loop B, that I'll call it loop C, then I find out that although the loop C has a much larger area than B, but the number of field lines being enclosed by loop C is the same as the number of field lines enclosed by loop B. Both of them encloses only 1, 2, 3, 4, 5, 6 field lines. So therefore, as a measure of the number of field lines enclosed in the loop C in fact has the same number of loops B as the flux, as the value of the flux. So therefore, you will need to know that the last case actually has the same magnetic flux as the case 2. So therefore, when you are using the value of A here, we need to be very careful. It's not just to naively put in the size of the area of the loop to this equation. Instead, what you're supposed to do is that you only use the area of the loop which has magnetic field lines passing through. So sometimes people will say that it's called the effective area of the loop, or I think maybe a better way would be to write it as the area of the loop inside the field. So therefore, those regions right here and here, they are not inside the magnetic field. So therefore, we will not consider them. Okay, so it's quite important to have this intuitive understanding because the mathematics here is actually quite limited. We can never just rely on the symbol and then tell me everything. We also need to be aware of the context behind. Now, then if this is true, then can we try to see whether this definition can also take into account of the cosine theta we mentioned. So for example, now I have another loop, we call it loop D. So the only difference between loop A and loop D is that loop D is like tilted. Therefore, this area is like this. This is loop D. These two, they have the same area. Now, then in this case, you find out that the difference between loop D and loop A is that normal is different. Loop A is having normal like this, and loop D, the normal will be like this. In the fact that here, theta will be like 0 degree. But for here, theta, let's make it simple, will be 45 degree. As the angle between the ray, not the ray, they look like the ray, but the field lines and the normal. This one has nothing here. Theta is just 0 in here. What is it? Now, so now there was a difference between the two. Well, we can look at the definition. Go back to the definition. Phi of A will be BA cosine, but for A, this will be cosine 0 degree. So therefore, it will be equals to B times A. While the phi of B, the phi of D will be the same field and then the same area A, but you have a 45 degree there. So therefore, cosine 45 degree is around like 0.71. So therefore, this will be smaller than the magnetic flux at A. And then you will find that there's also, well, therefore, the magnetic flux in this case will be smaller than the magnetic flux in this case. Well, according to the mathematics, the reason why it is smaller is because there's a cosine theta here. Well, then if we forget about the mathematics, we refer to the intuitive understanding that flux is a measure of the magnetic field lines enclosed in the loop. Then this simply means that you are now having a loop because it is tilted. Now it encloses smaller number of field lines. So therefore, for example, you can see if the loop is horizontal, it can enclose 2 field lines. But if the loop is not horizontal but tilted, then this loop can only enclose 1 field lines. Well, how about in the extreme case? The thing about it, if I have the theta equals to 90 degree, then how many field lines can it loop? Intuitively, this is not difficult to understand, because when you continue to turn the loop so that now the loop is vertical, and that means now this loop is not able to enclose any magnetic field lines. With the normal to be here, then we will have the theta to be 90 degree, because this is the ray and this is 90 degree as a theta. So therefore, we get theta equals 90 degree. Then the corresponding magnetic flux will be, you still have magnetic field, yes. You still have the area A, yes. But you do not have any value because you are having a factor of cosine 90 degree, which is 0. So this makes a lot of sense because it does not enclose any field lines. So that is the reason why mathematically we need to introduce such a factor in it, or we need to have such a factor in it, so that we can have the magnetic flux being a measure of the number of magnetic field lines enclosed in a loop. Okay. Now, finally, let's put a remark on the terminologies. So far, we will call B as the magnetic field strength. We also use the Tesla T as a unit of magnetic field strength. And this Tesla is also well defined. You remember 1 Tesla means using It's well defined because we have an equation that the first time we see the symbol b in the equation will be f equals to BLI sine theta. So therefore, what is magnetic field B? Will be the force per unit length per unit current when they are 90 degrees with each other. So everything well defined. Related equation here. But now, we have another equation related to B, which is the magnetic flux. We can write B equals to magnetic flux per area cosine theta. So therefore, we are able to relate the magnetic field strength as like a flux, like a magnetic flux in the numerator. Divided by some effective area in the denominator. And then we call this magnetic flux density. Just like population density, we talk about like how many people are living in a certain area. Then this is what we call magnetic flux density. So therefore, starting from today, or you look at some of the past paper question, they will call magnetic field B as another name. They call it magnetic flux density. While the unit of the magnetic flux density will be, well, we look at the unit of magnetic flux, which is the Weber. And then we look at the units of area, which is meter square. So in the denominator, so meter minus 2. So therefore, we now have a new name for the magnetic flux density. So therefore, this is what we introduced it as a new physical quantity. We call it magnetic flux. And then now, this is a bit abstract. You see, it's like I'm teaching you mathematics here. Well, yes, it's actually quite an abstract concept. In fact, we are calling this loop. It can even not a loop made of any material. It can be just a loop that you imagined that is an abstract object that in space. So, however, when this loop is not a abstract object, for example, it can be just a real loop made of conductors, that it can even have many loops. So for example, it can have a loop that have few number of turns, like this. It has n as a number of turns. Let's say 3 in this case. Then for each turn, there is essentially just one area there. So for example, at the back there is one area, and then at the second loop there is another area, and the last loop there is another area. Like this. Wow, this is so funny. At the last loop there is a last area here. So therefore, in total, there are the total flux we should consider should be equals to 3 times of the flux of each loop. So it should be equal to n times phi. and we don't call this total flux, we give it another name. We call it flux linkage. But essentially, it just means n, which is the number of turns of a loop, times the magnetic flux for each loop. This will be, we say that, oh, this is the magnetic flux linkage of the coil, for example. Then we will use this kind of language. Well, so finally, this is what we need to learn for the mathematics. Now we are ready to write down the mathematical formula for the electromagnetic induction. Electromagnetic induction is the following. You have is so-called Faraday's law. We only have learned one Faraday's law, so this is the Faraday's law of electromagnetic induction. And the mathematics is E equals to minus n d phi dt. It is how usually the textbook is written, but I will suggest just call it like this. Now what is this? First of all, this is our target. Remember, our main character is this, EMF induced. This E is the EMF induced in a loop or in a circuit. And then on the right hand side, then you have the rate of change of magnetic flux. Now what's this going on? Now we have on the top, this is just a change in magnetic flux linkage. Just like after minus before. And then delta T is the time taken for that change. So when we say you are talking about a change in something over the time taken, then the whole thing is the rate of change. So rate of change of magnetic flux linkage. And it turns out that Faraday's tells you that the EMF induced is just equals to the negative of the rate of change of flux linkage. So this is essentially the Faraday's law. So they put it in this way: EMF induced is directly proportional to the rate of change of the flux linkage. Historically, they use the term directly proportional because, in fact, there is a -1 in it. Okay. Now, okay, so you say there is a rate of change. So for students who take M2, they may ask, is this differentiation? Finally, we need to use differentiation in physics. Well, it turns out that no, we will still not do any differentiation. However, then how do we really interpret and apply this? Because this is obviously a change in, well, there's obviously a differentiation, right? But it turns out that we will not differentiate anything. We just understand it as the gradient of a graph. So this one should remind you like change in velocity. This one will remind you something that's kind of recall. For example, we have learned that in book 2, the acceleration is the change in velocity over change in time. Okay, and we also did not do any calculation. We did not do any differentiation, but we understand this as acceleration is the gradient of velocity time graph. And we also understand it as, do you still remember? The area of velocity, the area of acceleration time graph is the change in velocity. If this is not that obvious, maybe I take another alternative path. Is that, so I can write this as delta V equals to A times delta T. But this A times delta T can be written as the area of the AT graph. So this is what we have kind of learned in long time ago. And therefore, we will apply the same logic here. So we will say that the EMF induced is the area, is the gradient of magnetic flux linkage versus time. Just, you can see this is just this one, and this part is just this one, and this is this one. But there's one exception. There is a minus sign in here that you need to be aware of. So therefore, let's put it properly. So therefore now, the equation we're saying is E equals to minus change in flux linkage over change in time. So therefore, for the first one, then we will say, I think I do not have enough space to put here. So we'll say that EMF induced is minus 1 times the gradient of magnetic flux linkage time graph. Conversely, this can be written as the change in the magnetic flux linkage will be equals to minus EMF times delta T. Then we will call this, or we will interpret this as the change in magnetic flux linkage is the negative 1 times the area of EMF induced time graph. Now, of course, it's like a symmetric one, but I can tell you that 99% of the time is just the first case. This one I think they seldom talk about it. But okay, so therefore our bottom line is we need to learn how to apply this one. So let's make an example then before we end. So for example, I have a region of magnetic field. So this is a region, and I have a region, and this region is filled with magnetic field. Yeah, okay, let's use this one. I have a region of magnetic field. Okay, why does not fill? Do again. Okay, good. The region with magnetic field. So this is a B field. Let's suppose just for concreteness, we call it B into the page. So we call into the page, into the page, into the page, into the page. And then I have a coil, and this coil is entering the region. And I just call it the coil A, and then the area of the coil is A. And then this coil is moving towards this region of magnetic field. So therefore, as this coil is moving, you will have this entering the field, and then it will be the case that it's like completely inside the field, and it will be like leaving the field, and then completely leaving the field, like this. And these are the instant of time that you find out that the only thing that is changing is actually the A. Because you look at the magnetic flux linkage, this would be N times B times A times cosine theta. And then here, N does not change, N is just 1. B does not change, B is just constant. A will change with time because A is 0 at first, because none area, although the area of the coil does not change, but there is no area of the coil that is inside field. As the coil enters the free field, then there are an increasing number of area that it will be in the field. And then when the area is within this loop, then the A does not change, because no matter the coil is here, here, or here, the area inside the field remains unchanged. So it only decreases when the coil is leaving, and it decreases to 0 when the coil is completely out of the field. So therefore, only A is changing. So therefore, as a function of time, the N phi should start from 0 because A is 0 over here, and then start increasing and then stay constant, and then decreases back to 0, and then 0 again. So this refers to the instant line, I don't know how to call it, we call it 1, 2, 3, 4, 5. Just 1, 2, 3, 4, 5. These are the stages. Okay. Now, well, there is a change in the magnetic flux linkage. So, according to the Faraday's law, there should be a EMF induced. Because EMF induced is equals to the negative of change in magnetic flux linkage over time. Therefore, what we're doing now is just a gradient. You just look at the gradient of the graph above. So this is, and it means E is negative 1 times the gradient. So we just need to, in order for us to deduce the EMF at different stages of time, we just need to find a gradient. Today we see there's no gradients, there's a positive gradient, there's no gradients, that means zero gradients, and then there's negative gradients, and then there's a zero gradients. So, right, therefore it means that there's a positive and negative gradient, so let's put it here. Okay, and then therefore I will got zero gradients. And here there's a positive gradient, so this is positive. Remember there's a negative sign if the number to multiply to it, so therefore it will stay negative. And then for stage 3, you got zero gradient again, so therefore 0. And then stage 4, you have a negative gradient here, so multiply another negative one, so it becomes positive gradients. Yeah, I think I make it too high anyway, right here, like this. So therefore positive gradient, and then zero gradient again. So therefore, what do you see? You see that only these two period of time. That means only this and this period of time, there will be EMF induced. And this is how we apply the Faraday's law, or understand the Faraday's law. Well, we will take some time to elaborate further next time, but let's just stop it here first. But before we stop, I want you to think about referring to this case or the situation we also covered in the lecture. Is this the same what we find in the past? Previously, before we learn any mathematics, we saying that if there is a cutting of magnetic field lines, then there will be EMF induced. Or when there is a change in the number of field lines enclosed in the loop, then there will be EMF induced. Well, now mathematics tells us that you have EMF induced here and here. Well, is this the same coincidence that there is a cutting of magnetic field lines? Is there any cutting of magnetic field lines only in 2 and 4? I think yes, right? Because the magnetic field is here. So therefore, only when the coil get in, there will be cutting magnetic field lines. There will be cutting magnetic field lines here as well. Well, outside there's no field lines, so no cutting of magnetic field lines. But how in between? We may say, hey, I also have cutting magnetic field lines in stage 3. Why there is no EMF induced? Well, because it's kind of cancelled out. Because for this part, it's a cutting magnetic field lines in this way. Well, for this part, it's also cutting the magnetic field lines. They cut the magnetic field lines so that the number of field lines enclosed in the coil remains unchanged. So therefore, there's no EMF induced. So similarly, for 2 and 4, there is a cutting magnetic field lines, but the way it cut is it will increase, for example, for 2, it will increase the field lines inside the loop. For 4, it decreases the field lines inside the loop. So therefore, there is a change in the magnetic field lines enclosed in the loop, but from 2 to 4 in between, then there is no induced EMF. So that's why we find this result, there's no EMF induced in stage 3. So therefore, you say that cutting a magnetic field line is actually not a very good interpretation, although it's easy to understand. That's why we also introduce it, but it's not a complete picture. What a complete picture will be, we should looking at like the change in the magnetic field lines enclosed in the loop. But we also sometimes that it's not really easy to imagine a loop. You remember another question we did in the past is like we did not have a loop, we just have a wire. Then it doesn't have a loop, then how do you consider this? Then we will be more convenient to use the concept of cutting field lines. But never mind, the mathematics is coming to save us, to give us a vigorous way to talk about electromagnetic inductions. So, okay, anyway, then 4 pages or I think I want to keep it every time when I finish 4 pages I will end the video. Now we continue next time.